Run your hand along the flank of a premium car or the casing of a high-end laptop. The metal and plastic feel continuous. To human skin, it feels like a single, unbroken object. But turn on a harsh spotlight and sweep it across that exact same surface. Right where your hand felt perfection, the light breaks. The reflection shears off into a jagged, broken line. The object is deceiving you. The separate panels are geometrically joined, and to a physical touch, the transition is flawless. But to a beam of light, it is a collision. If you spend your time reviewing shaded CAD views or standard screen renders, you will never see this defect. Those tools average out the lighting, actively hiding the geometric flaw while you work. What we perceive as a single solid shape is actually a fragile patchwork of mathematical panels stitched together. The quality of those invisible seams dictates whether the final product looks like a luxury item or a cheap knockoff. To understand why the light breaks, we have to look at the exact math used to stitch those digital panels together. This animated diagram shows the most basic connection, called G0, or position continuity. The edges of two curved panels touch, successfully closing the gap, but their angles do not align. It creates a distinct sharp corner. Upgrade that connection to G1, tangency, and the slopes of the panels adjust to agree. The sharp corner disappears. If you ran your thumb over a physical G1 seam, it would feel perfectly smooth. Go one step further to G2, curvature continuity. Now, not only do the slopes agree, but the exact rate of the bend matches flawlessly across the join. The radius becomes perfectly uniform. Surfacing teams stress test these mathematical connections using zebra analysis. It is a simulated environment that projects harsh black and white stripes onto the 3D model to see exactly how light will behave. Under zebra analysis, a G1 connection fails instantly. The stripes might line up right at the seam, but they veer sharply away from each other the moment the underlying curve tightens. Only at G2 do those reflected stripes run continuously through the seam. The transition happens without a single kink or wobble in the optical pattern. That is why achieving a Class A surface in industrial design is an exacting standard of aesthetic reflectivity under light, rather than a standard of physical shape. Out in the manufacturing pipeline, producing a high-gloss injection molded part requires a diamond-buffed tool. That highly polished steel acts exactly like a mirror, amplifying every hidden geometric flaw in the plastic underneath it. If you specify a matte or textured finish instead, that exact same tool grade isn't required. The rough surface actively scatters the light, masking flow lines, hiding knit lines, and minor structural defects. The pipeline conflict happens because the decision to make a product gloss black is often made late in the development cycle. That call comes from the color and materials team, who operate completely isolated from the engineers building the geometry. The brief says gloss black, and that late decision retroactively forces an expensive G2 mathematical standard onto a 3D model that the geometry team originally built and approved at a simpler G1 standard. Upgrading that existing model to G2 causes a cascade of costs. The surfacing team has to generate an explosion of tiny patches to maintain tighter boundary controls, resulting in a heavily restricted, fragile digital file. Demanding higher continuity makes the 3D model incredibly rigid. The geometry becomes economically disastrous to alter at the exact moment a product program is most likely to request late-stage proportional changes. The jagged reflection on the final product is not a mathematical error. It is a process failure, caused entirely by allowing a downstream material decision to quietly dictate an upstream geometric standard. The reflex reaction is to demand maximum G3 continuity across the entire product just to play it safe. But calculating that level of geometry everywhere requires immense control and wastes months of pipeline resources. The actual solution is to define the material finish family at the earliest concept phase. Naming the finish establishes the required continuity class up front, before the first digital panel is drawn. This monochromatic render highlights the exact strategy. You selectively apply that expensive, high-level math only to the prominent crests and upper seams, the specific areas that will actually catch and carry a light reflection. The side and bottom seams can safely remain mathematically simpler. Because they live in shadow, they only need to pass the physical test of feeling smooth to a human touch. Design decisions are cheap as a sketch, brutal once tooled. See every angle before you build. Depix design intelligence. Mastering industrial design requires treating light, material, and underlying geometry as a single, inseparable system from day one.